Hi guys, today we're going to be doing a extra credit assignment on for EMAC 303 on Fourier transforms. So Dr. Turnquist talked about um, working on the transforms with sound and compressing sound files. This led me to researching that and deciding that I wanted to look at image files and how Fourier transforms can be used with those. So they can be used to uh, compress files, but they also can be used to analyze files. So today I have some code I've written up that's going to look at analyzing these images using Fourier transforms. So I'm going to run this first part for us. All right. So the goal is we're going to so this image, this is our original image, can be expressed as weighted combinations of sinusoidal, horizontal, and vertical frequencies. So that's what we're going to be looking at with the Fourier transform today. So the first thing we do is we just read in our image, and then we're just going to plot that original image, and then we're going to apply a Fourier transform to that image. So that's what this FFT2 does. And then this S, we're going to look at the magnitude of the frequencies, and then we're going to plot this as this one. There's too much data to display, so when we use the Fourier transform on a finite discrete pixel values and over a two-dimensional grid, we got too much data to display, leaving us with this dark graph. So this graph has has frequency in the y or in the x direction, going from 0 to 2 pi on this axis, and on this axis it's also going from 0 to 2 pi. So the first thing we're going to do is we're going to center this, and so instead of going from 0 to 2 pi, we're going to go from negative pi to pi with 0 running through the middle, and then negative pi to pi and 0 running through the middle. So here in the center of this image we will have 0, 0. So that's shown in here by just using this FFT shift, so you'll have your lower frequencies closer to this 0, 0 in the middle. So then we get this after plotting the so in the code we're going to take the log of it so we can see or visualize less data, and then analyze it. So then we are going to plot the log of the Fourier transform, and that's what we have right here. So for this triangle, obviously there are streaks going through the center here. So these streaks represent the edge of a line in the image. So they run parallel to each other. So if we had our original image was a square, we would only have two lines because the two lines or the four sides that make the square, two of them are parallel. So you would have two different edges. And that's what would be shown in this log of the transformed image. Now, these vertical frequencies here can be represented as a horizontal line on the original image. So you can see here that we have a horizontal line right here in our original image, and that is represented by this vertical frequency right here. Then what we do in our code is we're going to reconstruct the image. So we're just using this program, IFFT shift, and we're going to reconstruct it, and then we're going to take this reconstructed thing, hit it again with the IFFT2. So that's the inverse fast Fourier transform 2. And so that's going to redo. So this is the inverse shift, and this is the inverse fast Fourier transform. So we're taking this that the shifted fast Fourier transform, and we're going to inverse shift it, and then we're going to inverse transform it. So then we are left with our reconstructed image that is shown right here, and it is the same as this one with minimal compression from the Fourier transform and the inverse Fourier transform. So if I zoom in here, you can see that there was already a bit of pixelation, but it's a little bit darker here, and the image was altered, but very minimally. So going back to the log of the transformed Fourier image, we have the 3 lines representing the 3 different edges in the picture, with this one being the horizontal being this one, this negative slope being this one, and this positive slope being this one. So we're going to look at some different shapes. So X out of here, and then here's one of a hexagon. So you know how earlier I talked about parallel sides and how it would not give you would get 2 edges that are parallel, so you would not get repeated. I gave the example of a square. We have done that here with a hexagon. So obviously these edges are parallel, so then there's not streaks there. And earlier how a vertical frequency represented a horizontal line, this horizontal frequency represents this vertical line. From that, we can tell what the frequency of the edges are, and this right here being 0, 0, and we can see that this image contains more low frequency information than high frequency information because it is closer to this 0, 0. And here's our reconstructed image. Now, I also did this for an image I've taken, and so we just have an extra image right here. So you cannot do the fast Fourier transform on a color image. So in this code, the first thing I did is I had to use this RGB to gray to convert a color image to a gray image. So then I took the Fourier transform, centered it, and took the log transform. And let's see if we can zoom in on it, or I guess we're fine. But so earlier, talking about these almost horizontal lines representing vertical lines, I chose this photo because of the geometry, and it had lots of almost vertical lines and almost horizontal lines, and those are represented in this frequency graph by these almost vertical and almost horizontal lines. So from that we can see all the edges. This is so what this is used today is a lot of it is used for edge finding. So with in computer algorithms, by using fast Fourier transforms and looking at frequencies, you can pass either low frequency or high frequency filters, and from that we can blur images and also find edges. This is useful for graphic design and other computer programs where you might look at edges or decide boundaries in programs. Thank you. That was my project.